The World Finals of the ACM contest, I guess, are tomorrow. I encourage you to all watch and root for the Stony Brook team. Okay, we're not going to win, but I encourage people to root anyway. Where do we? Does anyone know how to monitor the teams? Out of curiosity, there's got to be a way to do it. And does anybody have an idea of what time? If it's 9 in the morning in Stockholm, what's it going to be here? Does anybody have any ideas? You guys are what? GMT what? +8. And if I say time in Stockholm, just tell me anything. That's +1. Is that right? Wait, is that right? So +8. So what does that mean for, I see it's 4 in the morning there now. So for it to be 9 in the morning, it'll have to be, I guess, right, we need to add another 5 hours to that or something like that. And so that takes it about 6 in the afternoon. Well, 5, 6 in the afternoon. Okay, so I encourage everybody to watch and see how we do and how your favorite teams do. Any questions about the World Finals while we're here? Okay, and maybe next year you guys will make it. Okay? Any other questions before we get into, actually, is this, I'm just curious here, is this does this actually go someplace like to a scoreboard? Oh, okay. So there was some kind of a challenge. I don't know what this means. Does anyone know what this means? Some kind of, oh, I see, this is some other kind of game that they had. And did Stony Brook do anything there? Doesn't look like it. Okay. Nonetheless, hopefully we'll cheer for our team. Okay, any other questions about the World Finals? Okay, any questions about, let's go back there. Any questions about the 100 problem read? How many people have started the 100 problem read? Okay, who have not started it? Okay, how long have the people, who's gotten half of it done? Okay, you said you got half of it done. Have you got all of it done? Half. How long is it taking you to get halfway done? 3 or 4 hours only. Okay, and was that in one block?
Well, firstly, I've done about more than 10 problems. Not yet 20, and then here is you can 30.
So what's your total time that you spent to get to half of it?
4 or 5.
4 or 5 in how many sessions?
4 or 5.
4 or 5. Okay, for those of you who haven't, and what about you? How long did it take you?
I think it's similar.
Similar. Okay, so we know roughly what the pace that this is, but the important thing is the number of sessions is reasonably large, because I gather you go bonkers after a while. Is that right? Okay, so get playing on that. Any questions? Okay, any other questions about any of the problems or anything we've done up to date? Okay. Last week there were the graph algorithm problems. Let's just tell you, like, how many people of the graph algorithm problems? How many people got all 4 of them? Okay. How many people got 3 of them? 2. How many people got 2 of them? 2. How many people got 1 of them? How many people got none of them? Okay. Good. Okay. So today I'd like to talk about is one of my favorite topics in the world somehow. I like dynamic programming a lot, okay? Dynamic, as an algorithms person, I have found that dynamic programming is one of these things that has the property that once you understand it, it's very simple, okay? But a lot of people don't understand it. And so it's good for giving you a certain amount of what I will say magic powers, okay? What is a magic power? A magic power is something you can do that other people can't do. Okay? And I have found that dynamic programming has over the years given me more magic powers than most other things. Okay? And so I do want to go through and explain it. How many people here feel they know about dynamic programming and they're pretty good at it? Raise your hand. See, one? Okay, it's not. Don't be shy. How many people feel they know about dynamic programming and are not very good about it? Okay? And how many people don't feel they know about dynamic programming? Okay. So, what is dynamic programming? And again, I'm going to spend most of my time on a fairly standard example, which is the edit distance thing. Okay? But which I'm sure many of you have seen before. But the important idea about it is that it is a way of solving what I tend to think of as optimization problems on things that can be ordered from left to right. Okay? Things that are ordered from left to right include character strings. Character strings have a left end and a right end. Trees can be ordered from left to right. Okay? If you take a tree, you can put things down. You can draw a tree in a certain way. If your tree has a meaningful ordering from left to right, like the leaves from left to right, dynamic programming can be done. Okay? Certain geometric problems. Sometimes the left to right ordering makes sense. Okay? Has some meaning to it. If so, then that can be worked on often with dynamic programming. We've seen a couple of examples so far of dynamic programming in action. We saw it when we were computing the binomial coefficient function. We talked about combinatorics. We talked about how to compute binomial coefficients using the Fermat's last theorem recurrence, right? And we showed that we used that as an example for how you evaluate recurrence relations. Okay, basically you're going to be building a table. You'll be storing the small values, and you'll be slowly working up bigger and bigger values to do it. Floyd's all-pair shortest path algorithm, which I think we talked about in our last week's activity, is another classic example of dynamic programming. Okay? Where, again, we tried to compute what were the number of paths, what was the length of the shortest path from I to j, using at most vertices 1 through k as intermediates. Okay? And again, we were able to do this for larger and larger values of k by using stored results. That is the basic idea of dynamic programming. Any questions? Okay. So the motivation for dynamic programming is to note that in many optimization problems, the greedy algorithm does not work, okay? So one way that someone might think about solving the shortest path from here to there might be to find what's the shortest road I can get on and go there. Okay, or it might say, well, let's just think about it. If we were looking at what would be a greedy shortest path kind of an idea? Okay? If we were thinking about it, can anybody think of an application where a greedy algorithm for shortest path, let's say, makes sense? Okay? In a graph, the one that I talk about here, where you start from one node and you walk out the shortest edge, that probably doesn't make any sense. Okay? I think everybody can see that they're going in the wrong direction. But what about, let's say, one where the points were in the plane and we have edges between certain pairs of points, right? Perhaps a more sensible greedy algorithm might be, take the step that brings us closest to our goal. Does that make sense? That now seems like a natural way that one might think about walking through a geometric network. Okay? Given a set of from your points, find all the places where you can go in one hop and go to the place that's closest to the world, to your goal. Okay? The good things are that a greedy algorithm is natural. The bad thing is that in the absence of a correctness proof, it is usually wrong. Okay? So if I give you a general graph, a graph containing a subset of edges of this geometric graph, and ask you to do that shortest path problem, walk towards the goal, that will usually be wrong. Okay? There's no guarantee that that will be right unless that graph has special properties to it. Okay? Can anyone give me a property of the graph that I just defined that would suffice to walk towards, to find the shortest path to the goal? So just to remind you what I'm saying, because I'm making it up as we go along. I give you those set of points in the plane. I define a graph over a certain set of points, where I connect each point to a certain other set of points. Okay? And I now want to find where, if I repeat, go to the point that gets me closest to where I'm going. Okay? Then it will give me the correct answer. Okay? Could someone give me an example of a graph I could define on this point that would always give me the correct answer? There's a trivial answer here, and then a more interesting answer, actually. Okay? Since no one's saying it, I'm confusing everybody. Obviously, if I define the complete graph on all the points, right? Then for any point that I wanted to go to, there is an edge that will get me there directly, right? If that was the graph, then this greedy algorithm would be the right thing, right? But that's obviously a pretty silly graph, right? In fact, there is a smaller graph that will do that property, which happens to be the Delaunay triangulation, which we'll talk about when we get to it in computational geometry. But the argument here is to prove that actually gives you the right answer. Requires a proof. Usually greedy algorithms don't work unless you have a proof. Dynamic programming is what does two things that are good for us. Okay? It systematically searches all possibilities. This is why correctness is usually pretty easy to show in dynamic programming. If we're checking all possible possibilities and we're picking the best one, then it's got to be correct. The neat thing about it is that by storing partial results, we avoid recomputing, and that is the efficiency gain. Okay, any questions? So that's probably all pretty big. Okay, so what dynamic programming algorithms are defined by are recurrence relations. And we talked a little bit about recurrence relations when we got the combinatorics. Okay? The truth is that dynamic programming algorithms, I say, are defined by recurrence relations. Now, there are a lot of different recursive algorithms that we see that are not seeming, they're still recursive, but they don't seem to be defined by recurrence relations. If we think about depth first search was a recursive algorithm. Okay? You started from one graph and you went to a place, and then you did a depth first search from a smaller algorithm. The reason why depth first search was efficient, okay, is that it avoided visiting things that we had already visited. Okay? If I just took a graph traverse and I say, okay, here's a place, visit it. Here's another edge, go visit it. I'll be trapped in infinite loops and things like this. The thing that makes depth first search efficient is that we maintain some state of what we have done, so we don't do it again. Okay, there's a certain level of storage that is necessary to avoid repeating things that we might otherwise do. We know that that's true in depth first search. We know that that's true in backtracking. Okay, we do things by systematically searching for things in a certain way. We maintain some state to avoid that we do the same thing over and over again. And really what dynamic programming is maintaining some state to avoid doing recursive things that we had already done once before. Okay? Any questions? This is all boilerplate, and I think that you've seen this level of description. But the key point in dynamic programming is that you start by hunting for a correct recursive algorithm and later worry about speeding it up by storing the results. Okay? First think about the recursive algorithm or the recurrence relation, and then worry about speeding it up. Any questions? Okay. So the classic mother of all dynamic programming algorithms is something that computes a function called edit distance. How many people here have seen the dynamic programming solution to edit distance? How many people have never seen the dynamic programming solution to edit distance? Oh, most of you. Okay. By edit distance, I mean string matching, approximate string matching. Let me ask another question again. How many people have seen the dynamic programming solution for approximate string matching? Raise your hand. How many people have never seen it? Okay, this is good. Then this is going to be new for most of you. This is good then. Okay? So, what I consider to be somehow the canonical application of dynamic programming to a problem that is very important that comes up in lots of places is something called approximate string matching. Okay? And the motivation for this problem comes up from the fact that it's often necessary to try to figure out how similar two pairs of strings are, or to transform one string to another. Okay? But let's think about string similarity. One thing that people would like to, that's a common thing to need to know, is knowing how similar are two things. Okay? Or where the differences are. So can anyone think of any applications related to text strings where, given a text string, you might want to know what's the most similar text string to it? Okay? Can anyone think of applications in the world where text string similarity comes to be an issue? Search engine. So how does it come into a search engine? Just be a little more precise.
You search in Google, it will prompt like, do you mean to search?
Oh, okay, so that's a good example. So when I type into Google, okay, you type in Skiena, and hopefully it will come back and say, do you mean Steven Skiena? Okay? Or perhaps it will say nothing. Maybe I'm not in it. Okay? But this is a question of similarity. You'd like to try to find out, given a bunch of strings, what is the most similar ones to it? Does everybody see that? I will put this in the general category of spelling correction. Okay? That someone types a spelling correction, types a word with a spelling correction, and you want to try to match it. Okay? Now, how do you think Google does this? Let's just stop and think about it. I don't think Google does dynamic programming on this. How do you think Google checks for spelling error? What was that?
I think the answer is yes. Yes is a,
I'm sorry, I didn't quite hear.
I think the answer is yes.
You think Google does use dynamic programming?
I think they use suffix trees.
Suffix trees? I'm going to guess that they use something called hashing, actually. That they're probably looking at everything that's within one change of this. So Google will be very good at finding things that are one change away from this, right? They're probably, but Google, and the way I suspect Google probably does this actually, is that they probably take all their words in their dictionary and that they try all different substitutions of one possible spelling mistake, okay? And they hash it into it, into buckets, and then they report these things. That's how I'm going to guess Google does it offline. Okay? But Google can get away with that because they're assuming there's only one spelling mistake per word. Okay? Has anybody ever seen Google correct something where they had two spelling mistakes? Okay? I will guess two spelling mistakes in one word. I will bet Google won't do that. Okay? You're going to try that now. I can tell you're burst into action. Okay? So the way I think it's doing it is with a hashing thing. Suppose we wanted to figure out, though, what the distance is between longer sentences or long words. Okay? For example, let's say we wanted to turn the biblical phrase, thou shalt not, into the modern phrase, you should not. There's a certain number of changes that are required to change this sentence to that sentence. Okay? And it might require, in this case, for example, two changes, thou and you, for example, require 2 changes, spelling changes, to make things happen, right? And if we interpret this as one word, it actually requires 5 changes to go from here to there, okay? And trying to figure out what the actual minimum set of 5 changes is, okay, is the hard thing to do. One change can be dealt with this kind of hashing thing. But the problem is if I say, allow me 5 changes, there are now entered the 5th possible sets of 5 changes, okay? And you end up getting an combinatorial explosion that way. Does that make sense what I'm saying now? How many people understand what I'm saying? And how many people are confused? Okay, good. Any particular question? Or just general confusion? Okay, so the idea here is, that's going to make string matching hard, is that if we want to try to convert, find the distance between thou shalt not kill and thou you should not murder, that's going to require a certain number of changes overall. Okay? Now, here you may get confused by saying, oh, these are separate words. Forget the fact that they're separate words. If you want to remove the blanks, the problem will stay the same. Okay? There's going to be a distance between this string and that string. And measuring how similar they are is the important problem of approximate string matching. Okay? And the way that it is naturally defined as the distance between 2 strings is to think of what's the smallest number of changes you have to make to get from thou shalt not to you should not. In fact, maybe let's go do that one out here. Thou shalt not, and you should not. What are the changes you have to make in order to get from here to here? Okay? We're going to define it by 3 possible changes you can make. You can change a character from one to a different. So the difference between shot and spot is 1 substitution of a character, an H for an S. Does everybody agree with that? The change, you could have the possibility of inserting a character into the pattern. There's sort of 2 strings you can think of. We'll call one the pattern and one the text. It could be that you can convert a go to a gog by adding a G here. Alternately, we can think about deleting a character from the pattern. We can convert hour to hour by deleting the H. Does everybody agree to see that? We could either delete an H here or insert an H there. They're symmetrical operations, right? But you've got to do, you might be doing a combination of an insert here and a delete here, which would be the same as a delete here or an insert and an insert there. But the possible changes are insert, delete, and substitute. And the question of finding the edit distance is to find the smallest number of changes you need to go from this to that. What are the changes we need to go from thou shalt not to you should not? If we're allowed to substitute characters, insert, or delete, then we want to propose a set of changes from here. What would we do to convert thou shalt not to you should not? Does anyone want to propose a way to do it? What manipulations must we do to this text string to get it to turn into that string? Okay? Someone give me what are the changes you need to do this? What? You want to say delete D, delete H,
or delete H or substitute T by U.
Okay, so deleting this and inserting the U would make 3 changes. A better strategy would be, as you notice, the T becomes the Y. That's a substitution, right? And you blow away the H. Now you've got those 2 together in 2 changes, right? What about shout and should? How many changes does it take to go from shout to should?
Change A to
You want to substitute an A to an O. That's a substitute.
Insert and
You want to insert a U. Okay? You could either delete this thing or you could insert a U. Right? And then do a substitute here. So that looks like 3 more changes would do it. Right? So the art of finding the edit distance is to figure out what the changes are to map one string to another. That's what we mean by finding the edit distance. Okay? And the interesting thing about it is to recognize that it seemingly is a hard problem. Okay? Because you've got to figure out which is the optimal set of things to do. Okay? Over the string, normally picking out the subset of changes to make would be a hard problem. Picking a subset of something is normally a hard problem. The difference here is that strings are going to be ordered from left to right. And that's why we're going to be able to use dynamic programming. Okay? Any questions about that? Any question about what I mean by edit distance? And how you can edit distance? Can anyone come up with an application for edit distance? Edit distance, computing the distance between 2 strings. The Google thing we saw was on a word-to-word basis. It was done by changing, just allowing one error message. So Google didn't really do dynamic programming. Who does dynamic programming? Can anyone think of reasons why you might want to compare a long text against another long text and figure out how many changes there were or where the changes were?
Checking spelling mistakes.
Checking spelling mistakes. Checking spelling mistakes might be right. Except again, I think that most spelling check programs limit yourself to 1 spelling mistake per word. Right?
And you can mix several advice which one is close to your.
You mean to suggest alternatives?
Suggestion.
Well, suggesting alternatives, I still think was probably done by this hashing scheme. That they had a list of all other words that were within 1 spelling change of this one. Okay? That wasn't really probably done by dynamic programming. What things are done by dynamic programming? You want to compare 2 whole texts to each other. Let's think about that. Can anyone come up with real applications where you're comparing texts together?
translation quality.
Translation quality. So you got people here who worry about. So what do you mean by translation quality? Let's explain that a little more.
A machine translation give you output, and you have some sample outputs.
So this is a good thing. There are a lot of people I know at this university who do research on machine translation, right? One way that you can tell how good your translation is, here you've got your Chinese string. Again, I'll write the Chinese symbols I know. There. Okay, that's Chinese, right? Okay? And, okay, don't ask me what it means. Okay. But there is a translation for what it means. 3, 2, 1. I think let's say exit. Okay? I don't know if that's right or not. But there's a correct translation. Okay? Then there is something that your system, this is known. This is known. But you want to check out how good your translator is. You're writing a Chinese to English translator. And it comes back and writes down, 1, 3, 2, exit. Okay? You want to know how many mistakes were made by your translator, right? The key idea here is you're going to align the output of your translation with the known gold standard and see where the mistakes were. And if you want to improve your translation, you care not only about minimizing, seeing what the number is, but seeing what the mistakes you made were. Does everybody see that idea? That's a pretty good example of where you would want to align text. Anybody come up with any other examples?
Checking plagiarism.
What?
Checking plagiarism.
Checking plagiarism, that's right. You guys say, ha ha ha, I'm going to go submit my program. I have a whole assignment due tomorrow. Okay? I don't have time to do it, but my friend does, right? But the teacher is not, is going to be running this, the teacher will, if you submit the same program, or you may modify it a little bit, the teacher is going to take your online program and his online program and submit it to a matching program. Okay? And what he is hopefully going to find out is that in fact there is a high similarity between your program and his program. So detecting, certainly programs are a little bit complicated. There's some different issues between programs. Let's say your term papers, English papers, right? If you're plagiarizing, it's clear there's going to be a lot of similarity between the words in these things. A lot of words will appear in the same order. That is the kind of a thing that you would want to find out by using edit distance. Okay? And they do similar things with program similarity testers. I'm just going to tell you this now because program similarity testers are maybe more interesting. Because in program similarity testing, certain things you can swap. Right? So you may think, aha, I can fool the the simulator by switching two lines, which really doesn't matter, right? They don't involve the same variable. Well, the truth is that these program similarity testers align parse trees. They don't align text. Okay? So they can capture you. You're doing all these clever things. You're saying, aha, I'm going to change the name of the variables, right? I'm going to say it said Fred's X. I'm going to change that to Harry's X. Now they're never going to catch me, right? Well, they will catch you. Because first of all, they are not going to be aligning the strings. They're going to be aligning the parse trees of the program. Okay? And they will relabel all the variables. Okay? But because parse trees are ordered, okay, they can find the canonical ordering and find the editing distance between these parse trees. They're going to get you. Okay? Any questions? So plagiarism detection turns out to be a good example of this. Okay? Comparing to a gold standard is a good example of this. I used to work for a while. I had a project where we built an optical character recognition system. And the issues were very much like you had proposed with this thing. We made guesses as to what the characters were. We wanted to find out what mistakes we made and what caused those mistakes. Note that a common problem would be in an optical character recognition system. Let's say you have NN. Maybe you would recognize that as an M, right? So if I have a long line of things, and it was NN, and I replace it by an M, that's really one mistake. But if I do it as an align, and if I just compare the characters straight, that one mistake would cause everything else to be called wrong after this. Does everybody see that? So trying to figure out what mistakes we really made, you had to do an alignment, okay? And that's what the edit distance stuff does. Any questions? We've gone on this long enough. There's also very important applications in biology for this kind of thing, aligning DNA sequences, okay? Any questions? Okay. So how do we compute the distance between two strings, okay? And what I want to tell you is that there is, and I'll give you an idea of a recursive algorithm for it. Suppose, let's look at the example here of Stephen Skiena and Stephen Skiena. Okay, there are a few possible ways, if we have the optimal alignment between them, something is going to have to be done with the last letters, right? In this case, probably the right thing to do is to say that they are matching each other, right? But perhaps it would pay to delete it, okay? Suppose, let's say that this was, let's say that the letter looked like this. The text looked like this. Instead of a match, it might pay to delete it, okay? Does everybody see that? There are a few possible things that we might want to do with the last part of our string. We could either decide to match it or substitute it if they're different. Perhaps this was a Skiena, an E. Okay, we may decide to do a substitution here. Or we might decide to delete this character. or we might decide to delete that character. Those are the only possible things we can do at the end. We can either delete one, delete the other, or substitute or match the last character of each. The recursive algorithm is going to tell us, we are going to figure out what the right way to do the alignment is by noticing that there are only three possibilities. Here's my code, okay? There's only three possible ways that the comparison of character string S and character string T, ending at positions I and J respectively, can end. We could decide to match the last character of each string, and we pay a cost of 1 if they differ, or 0 if they're the same. Or we could decide to delete the last character of the second string, or delete the last character of the first string. Which of these is the best option? You can't tell just by looking at the end. The best option is a function of the cost of that last operation plus the cost of doing the rest of the strings. So the total cost of ending on a match is going to be the cost of editing up until the last character on each string, I minus 1, J minus 1, plus the cost of the last operation. The cost of deleting, or we might edit all the first string into all but one character of the second string. If we know the optimal cost of that, plus the cost of doing that last deletion. Or we can delete from the first string, and the cost of that is going to be the cost of this operation plus the cost of getting to that state. Does everybody see that? The total cost depends upon getting the cost of doing everything up until the last character plus the cost of doing the last character. And if so, then the best way to end up doing the editing is to pick which one of these three operations have minimum total cost. Okay? Does everybody see that idea? You want to minimize the total cost over the three possible ways of ending it. Okay? And this can be done if we compute the costs recursively. Here's string compare, string compare, string compare. Right? There's a basis case. If one of the strings is empty, we have to pay the price of deleting, the entire remaining part of the string. Right? That's what this is saying. These are the basis cases of our recurrence. Right? If I have one string of 10 characters, how much does it take to align it to a string of 0 characters? Well, you've got to delete those 10 characters, right? So this gives us a recursive algorithm to compute the edit distance. Figure out the cost of each of the total cost of all three operations, pick the minimum, and that's the lowest total cost. Any questions about this algorithm? How many people sort of see it? How many people see why it is correct? Raise your hand. How many people don't see why it's correct? Raise your hand. Now tell me what the time complexity of this algorithm is. Okay? Does anyone want to take a guess when you look at this thing?
3 to the power n.
This is a 3 to the power n algorithm, or something like that. Okay? Where's the exponential thing going on? The exponential thing that's going on here is that this is a legitimate recursive call, right? What's going to happen when we build this thing for comparing two strings? If I have originally something of size, what do we want to think of the two strings? If the two strings are of size, 5 and 5, my three possible recursive calls from that are going to be 5, 4, 4, 4, 4, 5. When I work on this one recursively, I'm going to have 3 recursive calls. This is going to give me what? I guess 5, 3. 4, 3, 4, 4. Ding, ding. I'm recomputing the same thing I had before. Does everybody see that? Here again, what are my possibilities? It would be 3, 5, 3, 4, 4, 4. Ding, ding, ding. I computed it again. Right? In fact, when I ran this program, I could compute the edit distance between 2 strings of up to 12 characters each. And then my program took too long, because 3 to the n is a big thing, right? It's actually more than 3 to the n, actually, because it's complicated to figure that out exactly. Because but 3 to the n-ish. Let's just say 3 to the n-ish. Okay? The key insight here, though, is that we don't need to. We can in fact store things efficiently, because there are only s times t possible unique recursive calls. Notice that here and here we share the same recursive call, namely the cost of a prefix of length 4 against a prefix of length 4. The important thing to see here is that there are only, if the first one is that the length of the strings are s and t, there's only s possible values for the first one, prefix lengths for the first string, and t possible values for the second one. Okay? So instead of actually making the recursive call, let's build a 2-dimensional matrix where we explicitly store the cost of editing the first s characters into t characters for all values of s and t, as well as get back, as well as what we'll also call a parent pointer, showing us how we got to that. So I'll show you my dynamic programming version in a minute, but it's really not that much different than the than the recursive one. First, I keep track of a dynamic programming table where I keep track of the cost and the parent for every possible ij pair. Okay? And I'm going to, instead of making recursive calls, look it up in the table. I am going to keep track of a parent field, namely which way of these 3 possibilities was the one that I ended up following. Okay? Because that's going to help us later. Okay? And finally, I make it a little more general, because I'm going to be using writing it in terms of some abstract procedures, okay, that I'll explain in a minute. Okay? When you look at my code carefully, to try to make it cleaner, I did something with the string that some people find confusing. I padded both of the strings by blanks so that the first real character sits in s sub 1. As opposed to in a C string, normally arrays count from 0, right? Just because I felt it was easier to keep the indices straight. But here's my dynamic programming solution. Let's go through this thing. First of all, I'm going to initialize the initial row and column of my matrix. This is going to tell me what is the cost. If this is the S value, or basically I, this is J. This is going to tell me what's the cost of editing a string of length I into a string of length 0. Okay? This column here is going to tell me what's the cost of editing a string of length 0 into a string of length arbitrary size. That's what the initialization procedures are doing. In general, what am I doing? For every ij pair of the string, what I'm going to do is I'm going to say the optimal cost of getting from I to j, ending at I to j in a match, is the cost of the match of the last 2 characters plus the cost of the previous value, the prefix strings, which we already have in a table so we can look this up. We take these, we find which is the minimum of these three. Match, insert, and delete. And then I keep the cost as being the minimum of those three, and the parent is the operation, match, insert, delete. That is the optimum one. Okay? Any questions about that? Then, if we think of this as a matrix, there is a certain cell here that we care about. Okay? The cost of editing the entire string here into the entire string here. Our goal cell function is going to tell us where the optimal value is, which happens to be ij, okay, at the end. Actually, I guess it's the s of t, really. The goal cell will just return s of t. And return the cost of that. Any questions about that? Okay. How fast is this algorithm? Let's look at the time complexity of this version. What is it? Okay. Here, we are setting this s times t cell values. Here we're setting a linear number of them, or s plus t. Here we go from s to t. We do constant work, constant work, constant work. This is constant work times s times t. This is going to be quadratic in the size of the strings. Okay? Any questions about that? So for what size value of n could we compute the edit distance? Pretty comfortable. If I want to align two strings together, okay? How big a string could I do that with? Someone want to suggest a value of n?
1,000.
What?
1,000.
1,000 is a good, because 1,000 times 1,000 is a million, which is my usual belief as to what it is. Maybe you could do a little more than a million. Depends upon how clever you are, how big your machine is. But it's basically about 1,000-ish. Okay? Any questions? Okay. So this is the example of what happens when you edit "you should not" to "thou shalt not." Okay? What we end up getting, this is the cost matrix. I want you to just make sure you understand it. This is the blank. The cost of editing a blank to a prefix of length I is I. That's why these values are 1 through n, 1 through 14. Here we have the cost of editing a blank to a prefix of that. These are why the values here are 1 to 14. Okay? Any questions about that? In general, what we're going to do is fill in these values now in what I'm going to say, this kind of row major thing. Every value depends upon three other values. The value 1 up and 1 over from it, the value 1 up and the value 1 over. Those are the three possible values. So long as we have those values in the table, then we can go ahead and look it up. Any questions about that? Okay. So here is actually the cost matrix computed in "you should not" to "thou shalt not." What does this value of 5 mean? Actually, let's go and do something a little fancy. Oh, okay, a little disappointing. Okay. The value of 5 means that there is a transformation from here to here involving 5 steps. If we followed the parent pointers, what's probably going to happen is that, again, I'm going to try to follow it. I think the parent pointers end up going like this. And this. Okay? That this shows that in order to get a U, a T to a U, a Y, we do a substitution. That's the diagonal move, right? To get the TH to a Y at a cost of 2, we did a delete and a substitution. That's what that's saying. And then we could match the O, match the U, match the blank, match the S, match the H. We actually matched with a substitution, the O for a U, it looks like. By following through what these changes are, by working with the parents, we can see where were the changes that we actually made. Okay? Any questions? Going through the, the parents matrix gives us what those operations were. So here, it says that to switch from thou shalt not to you should not, what did we do? It looks like we did a deletion. We did a substitution. We did a match. How many matches in a row did we do? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. We then did an insert, which I gather was an O. We then did a substitution, which was the U. We then did a match, which was the L. We then did a substitution, which was the D. Where were we? Here, I guess. We then did match. And the claim was that this was 5 changes. 1, 2, 3, 4, 5. Any questions about that? So the value down here at the end should be the number of changes. The sequence we get by tracing back the parent pointers tells us what those changes actually were. Any questions? Okay. Now to reconstruct those paths, again, it's sort of a little bit like we talked about how you reconstruct a path from breadth first search. We went through that. Given this dynamic programming matrix, we want to walk backwards from the goal state to the parent state. Okay? By walking this back, the parent feature lets us do it. The trouble is walking from the parent, from the goal state back, gives us the parents, the chain of operations in the wrong order. By using recursion, okay, and figuring out what the last step was. The last step at ij, it either was a match, an insert, or a delete. If it was a match, what we'll do is we'll first reconstruct the path back to the previous state. Then output whatever we want to output for our match. Okay? By doing the full backward walk recursively before we do the local operation, we print the path out in the right order. Any questions? Okay? I feel that's not very interesting, but that's kind of important here. Any questions? Okay. So any questions at all about how you do dynamic programming for edit distance? How many people think they understand it? Raise your hand if you understand it. How many people don't understand it and want to understand it? Raise your hands. Okay? Now, the thing that I did that may have looked mysterious at the time, okay, was that I built my edit distance function on the basis of a couple of different, let's say, primitives that I didn't include in my code. Because it gives me a way to customize edit distance to do lots of different things. First of all, I give you the row and column initialization thing. What was the cost of matching I characters to an empty string? Okay? In edit distance, it was important it be I. But for other applications, perhaps you would want to set a different cost. In terms of minimizing the number of operations, I had what was the cost of transforming C to D, a character C to a character D, or deleting a character C. Okay? In standard edit distance, my match function would return a cost of 0 if they were the same characters, and 1 if they were different. But note that for a lot of applications of edit distance, you might want to have different penalty costs for transforming one character to another. Can anybody think of a different set of penalty substitution costs for characters, which might make sense if you, in certain applications, if you want to find the right alignment of things? Okay? Here, the standard way it charges 1 for substituting one character to any other character. Can anybody think of reasons why you might want to have a different cost function there? Let's say you were trying to correct for somebody's typing. Okay? Should you charge them 1 for every typing mistake? Or are certain typing mistakes more likely to happen than other typing mistakes? When some of you type fast, are you equally likely to make a mistake when you mean to type an S? Is it always equally likely what character you're going to make the mistake to? Or are certain characters more likely to be mistaken? What would be the more likely substitutions if when you type an S? If you typed it wrong, what would it be? You're saying a D or A, right? Because they're near it in the keyboard, right? What if it was a spelling mistake? When you substitute a character and a spelling mistake, is it equally likely that you replace every letter with another one, or are there often more logical substitutions? Okay? So for example, if you have a C, perhaps a C and a K are more likely to be misspelled, right? Because they make the same sound. Or an S. If you replace a C with a Q, that's probably not very likely, right? The way you could modulate your edit distance function is to charge different costs for different substitutions. And that turns out to be kind of an important thing to do in practice, depending upon what your application is. Okay? Any questions? So if you want to, what this is saying is that when there's a difference between configuring your algorithm and configuring your parameters. It should be clear that if you want to align different texts, okay, if you want to come up with what the real match is, if there are phenomena where certain characters are more likely to be confused with other ones, you would want to tune the costs of these things to get the alignment so that it prefers the alignments that make sense. Okay? That should be clear. Okay? And we've got that freedom because this is now a function. It's independent of the algorithm. There's another function I have there called goal state that will tell you where is it that the goal actually is. Okay? Where is the final answer? In the string edit distance, to convert this to that, the final answer was always in the last value of the cell of the matrix. Okay? But for certain dynamic programming problems, certain edit distance-like problems, that's not true. That the answer might exist someplace else in the table. Okay? And so enable me to generalize it by making that a function. Any questions? That may not yet be clear why I need it. Okay? Any questions? Well, the reason why I need it has to do with a slightly different version of edit distance. Suppose, let's say, I wanted to do substring matching. Okay? Let's say we have a world where we take a long text, let's say the Bible. Okay? I'm used to thinking about the Bible as a long book, right? And suppose we want to find out where Skiena is in the Bible. Okay? Now, I don't know how many of you have ever read the Bible before? Probably none. How many of you have ever heard of the Bible before? Okay? How many people think Skiena is in the Bible? No, it's not. Okay? It's not that. Not that. I read my algorithm. If you view my algorithms book as the Bible, then the answer is yes. If you view the Bible as the Bible, the answer is no. But suppose, let's say, we wanted to figure out where is this substring most closely represented in this long text, right? Perhaps there's some place in there where it talks about skin, you know, I want to skin a fish. I don't know if that's one, right? Or perhaps someplace in there they talk about somebody going skiing. I don't know if that's in the Bible either, quite frankly. Okay? But if you want to try to, we have a short pattern, and we want to figure out where does it best fit in the text. This is a somewhat different but clearly related problem to the cost of editing the entire string to the entire string. Suppose we did the edit distance, just like we did before, of Skiena in the Bible. What would happen? Can anybody guess what kind of an alignment would be returned? If you wanted to find where Skiena, if you want to edit Skiena into the whole Bible, what is going to be the best possible alignment you're going to find? All letters scattered. Is that right? The best possible thing will be delete everything up until the first S in the Bible. And then to delete everything up until the first K. And then delete up to the I, and then delete up to the E, and delete up to the N, and delete up to the A. Does everybody see that? That's not what we're looking for. Does everybody see that? So suppose you want to find where does this pattern most occur in the program. This has, like in the plagiarism example. If I wanted you to, let's say, align, if you're trying to hide, you have your plagiarized program that you're trying to hide in a compared to the real one. One way you could do it is to include a lot of irrelevant routines, right? Because if you just do imagine the whole thing to the whole thing, if one text is much bigger than the other, it's going to get washed out. So how do we find where is this the best place where this string occurs? Okay? How do we have to modify our edit distance to find this instead of the scattered thing? What? You say word by word match. I'm going to say no, because there's nothing really different between words and characters. Okay? If I delete all the words, it turns out in Hebrew they're not blanks.
Well, I mean, you just take out this word and you match with Skiena, not match, throw away and take another one.
Okay, you're saying something about word boundaries. As I understand in Chinese, you guys know about Chinese, but as I understand in Chinese, there's no blanks, right?
Yeah, no.
So if I were to do the same thing in the Chinese translation of the Bible, it wouldn't work, right? That's not a solution. Okay?
Similarly, you can, but there's still punctuals and other parts of things.
Okay, let's say I don't want to worry about words. In DNA sequences, there are no blanks and there's no punctuation. So that doesn't solve the problem. Okay? How do we modify, okay, the edit distance problem we saw to this question of local search? Okay? Any ideas what has to change? Okay? Let's think about it. Somehow, we've got to make it equally good to start at this point in the string than it did to start here, right? Because somehow, if it required, if the skin of fish was 1,000,000 characters into the string, we want a match starting from here to be as good as a match from any place else. Does that make sense? Okay? I'm not sure it's not clear to me I'm making sense right now to you guys. Okay? But what I want to claim is I need to make a few changes. I need to let my edit cert distance start at a position that is independent of the text. So that a match in the middle, that starts in the middle, isn't prejudiced against. And likewise, so the right alignment is not going to necessarily end here, but it's going to start someplace and end somewhere in the bottom row. I want to know what's the cheapest cost of matching Skiena, the entire Skiena, against some portion of the text, where it starts anywhere. Okay? Any questions? And it turns out this is all I need to change in order to make this match substrings instead of strings. Originally, my row init function initialized the cost of the top row to be 1, 2, 3, 4, dot, dot, dot. If I initialize the top row to all be 0, that the cost of matching an empty part of Skiena, an empty string, to the first I characters of the text, if I set that cost to be 0, the optimal alignment does not depend upon where in the text do I start. That's why changing the init made a difference. And what I want to now know is, my alignment can end anywhere in the bottom row, because it's the cost of aligning all of Skiena against, I want to know where, this is going to be, what is the cheapest cost of Skiena ending at this position. Okay? So I now have to check all possible values, okay, of the bottom row to find which was the cheapest. And that will give me the cell where the alignment ended and where I will work back from to see where the match was. Any questions? Okay, I can tell people are either lost or confused or bored. How many people understand these changes I made for substring matching? How many people feel they understand it? Few. How many people don't feel they understand it? Okay. How many people aren't answering? Okay, several people. Okay. Look at any algorithms book. Okay, be it mine or, of course, this thing has a nice description of it. Okay, to see why the substring matching works here. But the interesting thing is that it's a good example of how you change the edit distance function a little bit, and it computes something quite wildly different. Any questions? Okay. Any other questions? Last time. Okay. There are lots of other things that turn out to be interesting to compute here. One of them is called longest common subsequence. Suppose, let's say, I am given two strings, and I want to compute what is the longest scattered subsequence, sort of like the thing I was telling you I didn't want. Here I have Skiena. If I want to find what is the longest string such that the letters in this common subsequence appear in the same order in both of the inputs. Suppose that my string was Democrat and Republican. E, C, A appears in Democrat. E, C, A appears in Republican. That's a string of length 3 that occurs as a subsequence of both of them. It's scattered, but the characters appear in the same order. There is no such string of length 4 between these two words. Okay? So the longest common subsequence problem is to find out what is the longest string, which is a subsequence of both inputs. Okay? Any questions about that? What changes to edit distance do we have to make in order to compute this thing, to find the longest common subsequence? Okay? It's going to be like the first edit distance, because we're comparing the whole string to the whole string. So the goal is going to lie in the same place. But what cost function changes do we need to make in order that the alignment find what is the longest common subsequence between the two of them? Okay? Any ideas? Now, I wrote it here. If you're interested enough, you can read it. But any ideas here? If I want to try to align Democrat and Republican, well, let's try two other words. What would be two other words? Let's give some other example. Give me two words that have a long common subsequence. Oh, I think it's a good one. Any ideas? Give me two words that have a common subsequence between them. Okay. Hong, Kong, and something else. What would Hong? Hong and Kong is a good example, right? Hong and Kong have an alignment of length 3, right? But how would I find that alignment? In this case, what I would like to say is I want to reward myself for an exact match, but not reward myself for a substitution, right? So what if, let's say, I make the cost function where the cost of a match was 0 if the characters were the same, but infinite if there was a substitution. Then what would the alignment of two strings be? If the cost of doing a substitution is infinite, I'm not allowed to make any substitutions, right? I will only make matches, and everything else will be an insert or a delete. Does everybody see that? Every character, if the cost of a substitution is high enough, the cost of the optimal alignment is going to be exact substitutions or insertions and deletions. So then the cost between the two strings is going to be the length of the first string plus the length of the second string minus the number of the length of the longest common subsequence. Okay? Does everybody see that? If the cost of substitution is high enough, the only alignments it can be is going to be deletions and exact matches. And if we didn't allow any exact matches, okay, the cost would be the number of characters that we delete from the first string plus the number of characters we delete from the second string. Okay? The optimal alignment will be the string length minus the cost of the longest common subsequence. Any questions here? Another problem that's related is what we call longest monotone subsequence. Suppose, let's say, I gave you a set of numbers here. Okay? A longest monotone subsequence would be would be a set of numbers, a sequence of numbers that appear in order and are, increasing. How would we find such a thing? Given as input a permutation or a sequence of numbers, how do we find the longest increasing sequence of this? Okay? I can tell people are drifting. But basically, I will tell you it's a variation of edit distance. Okay? If you think about the strings right. What are the two strings here? One of the strings is the string of digits. If you want to think of it as edit distance, you need to come up with a second string. Okay? What is the second string here? Okay? If we compare the strings to the numbers sorted, then what's going to happen? Here we have the digit stream. Here we have the sorted digit stream. Sorted digit stream would be 1, 2, 3, 4, 5, 6, 7, 8, 9. If we now find the longest common subsequence between them, by definition, the ordered sequence is ordered. The longest common subsequence is going to be the longest string from here, such that the digits appear in increasing order. How many people understood that? That actually should have been understandable, right? Any questions? So by being clever, edit distance can do lots and lots of things. And it's important to understand it, especially because many of the problems we deal with this week will be of that flavor. One problem is about, there is a goal where you've got a bunch of elephants who have weights and IQs. And the question is to find a lot of heavy, find a sequence of heavy elephants. Okay? Elephants that are getting heavier and heavier, yet dumber and dumber. Okay? And that's I claim, if you think of it right, is an obvious edit distance thing. There's a problem here about stacking turtles. I don't know if any of you ever read the Dr. Seuss book, Yertle the Turtle. How many people have read that one? Again, you guys grew up with a different culture. But there's a question here of turtles want to get stacked up in a stack. And each turtle has a weight and a strength. And they want to know how big a tower of turtles you can build without breaking any turtles. Okay? That's this one. This other one is to solve a flavor of traveling salesman problem. We want to find a traveling salesman problem across a matrix, where the magic word is left to right across a matrix. And that should catch a whiff of dynamic programming. And finally, there's an interesting problem on there about ferries. Okay, I guess in Hong Kong, I know you have a lot of ferries here. Does anybody have any are there any ferries in Hong Kong where you're allowed to put cars on them? If any of you have seen this thing, this may seem like a weird thing to you, but it's not weird to me. I come from a place where there often are car ferries. So let's say here you have your island, and here you've got roads, and here you've got another island, and here you've got roads. Okay, instead of building a bridge, a fairly common thing would be to build a ferry that takes the cars from here to there. Does that make sense? And so when you get on one of these ferries, there's actually one of these very close to Stony Brook. You come and visit me, and we go to Port Jefferson, which is right near Stony Brook. There's a nice car ferry. And on that car ferry, a car ferry boat looks something like this. There are a couple of lanes on this car ferry boat. Okay? And in the problem, there's two. You have a long list of cars here. And you want your cars to sort of go onto the ferry boat so that you can ship as many pack the cars as tightly as possible on the ferry. Everybody see that? Well, one way you could do it, conceivably, is to load up this side of the car first. And then load up the other side of the car. The trouble is, suppose, let's say this is not a car, but this is a truck. Then it might be that you load this side, and now there's no longer room for the truck. Okay? And now that truck has to go over here. And now you start filling this side, all the space is unused. The question is going to be, how do you assign the cars to the ferry lines so as to maximize the use of the ferry boat? Any question about that? Okay, read that. You'll see what happens. And next class, we'll talk about these kind of things. Any questions about the dynamic programming? Look at it. Don't be afraid to look at the chapter in my book about the edit distance if this is confusing. Okay, because it's important that you understand that to give you a chance in some of these other problems. Anything else? Okay, if not, thanks for your attention, and I'll talk to you guys next class.